In 2021, Ford Motor Company left 40,000 pickup trucks sitting in parking lots across Michigan, fully assembled, engines ready, 0 buyers turned away. The trucks couldn't be sold because each one was missing a single semiconductor chip worth approximately $30. Those incomplete vehicles represented nearly $1 billion in frozen revenue from a $30 component. A piece of silicon smaller than your thumbnail nearly halted one of the largest manufacturing companies on Earth, and most people still don't understand how it happened or why the conditions that caused it are quietly rebuilding themselves right now. The chip shortage cost the global economy an estimated $500 billion between 2020 and 2023. That's not an abstraction. That's the price of the car you bought going up by an average of $10,000. That's the PlayStation 5 you couldn't find for 2 years. That's the hospital equipment that got delayed, the appliances that sat on backorder, the factory floors that went silent because a conveyor belt's control unit needed a chip that didn't exist. Every modern product that moves, computes, or senses the world requires semiconductors. There is no workaround. You can't substitute aluminum for silicon the way you can substitute one metal for another in a car frame. The chip is either there or it isn't. And here's what makes the next shortage more dangerous than the last one. The global economy is now even more dependent on chips than it was in 2020, and the geographic concentration of manufacturing has barely changed. Semiconductors are not like other industrial components. You cannot build a new chip factory the way you build a new warehouse. A modern semiconductor fabrication plant, called a fab, costs between $15 and $20 billion to construct, takes 3 to 5 years to become operational, and requires thousands of engineers trained in processes that have no civilian equivalent. The physics involved are extreme. A state-of-the-art chip contains transistors whose features are measured in angstroms, units so small that a human hair is roughly 1,000,000 times wider. To understand the supply chain's fragility, think of it like a single bridge over a canyon that every vehicle on Earth must cross. You can't build a second bridge in an afternoon. You can't reroute traffic through a field. And until recently, that bridge was almost entirely in Taiwan, specifically inside one company, TSMC, Taiwan Semiconductor Manufacturing Company, which manufactures chips for Apple, Nvidia, AMD, Qualcomm, and hundreds of others simultaneously. Here is the part that most people never learned. The 2020 chip shortage didn't start with COVID. It started with a miscalculation that cascaded. When automakers saw demand fall in early 2020, they canceled their semiconductor orders, freeing up capacity. Chip manufacturers immediately filled that capacity with consumer electronics orders, laptops, tablets, game consoles, because demand for those exploded as the world moved home. Then automakers realized within months that car demand hadn't collapsed at all. They went back to order chips and found the fabrication lines fully booked for 12 to 18 months. But here's what makes this structurally terrifying. Automotive chips are not the same as smartphone chips. They are older, cheaper designs fabricated on what the industry calls mature nodes. The advanced fabs built for cutting-edge AI processors cannot simply pivot to make them. The bottleneck wasn't a lack of chip factories in general. It was a lack of the right factories making the right chips, and that distinction matters enormously for understanding what happens next. Most people assume the CHIPS Act solved this. It didn't. The United States passed the CHIPS and Science Act in 2022, committing $52 billion to domestic semiconductor manufacturing. The European Union matched that energy with its own CHIPS Act. Japan, South Korea, and India launched similar programs. On paper, this looks like a coordinated global response. But consider the actual timeline. Intel's new fab in Ohio, originally promised to open in 2025, has been delayed to at least 2027 and potentially 2028. TSMC's Arizona facility, one of the most watched industrial projects in American history, ran years behind schedule partly because of workforce shortages. American construction workers and engineers weren't trained in the hyper-precise standards that Asian fab construction requires. Meanwhile, TSMC still manufactures more than 90% of the world's most advanced chips, the ones below 3 nanometers that power AI systems, in Taiwan. A military confrontation in the Taiwan Strait, something that American military planners rate as a genuine scenario within this decade, would not just disrupt supply. It would eliminate it. Entirely. Overnight. The mechanism behind chip manufacturing is genuinely unlike any other industrial process on Earth. Building a modern chip requires a technique called extreme ultraviolet lithography, or EUV. Imagine trying to write the complete works of Shakespeare on a piece of paper the size of a postage stamp, using a beam of light as your pen. That's roughly what EUV does. except the patterns being written are circuit pathways controlling electricity at the quantum level. Only one company in the world makes the machines capable of this, ASML, based in the Netherlands. A single ASML EUV machine costs approximately $350 million, weighs 180 tons, contains 457,000 individual parts, and takes a full year to assemble and ship. TSMC owns more of them than any other entity on Earth. No EUV machine, no advanced chip, no AI accelerator, no modern smartphone, no self-driving system, no next-generation military hardware. The entire technological future of the global economy passes through a factory in Eindhoven, Netherlands, and 2 fabrication complexes in Taiwan. That's not a supply chain. That's a single point of failure with a bow on it. The complications run deeper than geography. The workforce problem is acute and worsening. Semiconductor engineering requires a decade of specialized education, and the pipeline of trained professionals globally is not growing fast enough to staff the new fabs being built. TSMC's Arizona plant reportedly struggled to find enough qualified American workers and had to import engineers from Taiwan, triggering immigration complications that delayed the project further. There is also a financial problem. Chipmakers are cyclical businesses. When demand softens, as it did briefly in 2023 when the consumer electronics boom unwound, companies cut investment, lay off engineers, and scale back expansion plans. TSMC, Samsung, and Intel all moderated capital expenditure forecasts in 2023 and 2024, meaning the fabs that were supposed to close the supply gap are being built slower than projected. The geopolitical dimension adds a third layer. China controls the majority of rare earth elements used in chip packaging materials. A targeted export restriction, of the kind China has already demonstrated it is willing to use, could choke the supply chain from an entirely different angle than anyone's current contingency plans address. This affects you more directly than you might think. If you work in automotive, healthcare technology, defense contracting, consumer electronics, renewable energy, or financial services infrastructure, your industry's near-term growth is contingent on chip availability. The AI boom driving Amazon's cloud revenues surge right now. Headline news as of this week runs entirely on NVIDIA H100 and B200 chips that are supply constrained. If you're building a company, pricing a product, or making a career bet on anything that involves computing at scale, the availability and cost of silicon is a real variable in your planning horizon, not a background assumption. Analysts at Goldman Sachs projected in 2024 that AI chip demand alone will outpace supply through at least 2027. Watch the quarterly earnings calls of TSMC. Watch ASML's order backlog numbers. Those 2 data points will tell you more about the next shortage before it arrives than any government report will. Semiconductor supply is now the underlying variable of modern civilization in the same way that oil was in 1973. The difference is we understand